March 14, 1943, Rechlin-Lehrs Airfield, Mecklenburg, Germany. Oberst Wolfgang Vorwald stood before the device that would shatter every assumption German intelligence held about American bombing capability. The metal cylinder, barely larger than a football, gleamed under the fluorescent lights of the Luftwaffe's secret evaluation facility. Serial number 73-5-2-1 was stamped into the casing, identifying it as a Norden Mark 15 bombsight, recovered intact from a B-17 Flying Fortress shot down over occupied France 6 weeks earlier. This is impossible. Vorwald's hands moved across the gyroscopes, the mirrors, the calculating mechanisms with the precision of a man who understood optics and ballistics at a level few could match. No bombsight could achieve this level of precision. Not at 20,000 feet, not through cloud cover, not while the aircraft is taking evasive action. Yet here it was. The physical evidence contradicted everything German doctrine assumed about strategic bombing accuracy. The Norden Bombsight represented more than advanced technology. It embodied a fundamental difference in how America and Germany understood the purpose of strategic air power. For 2 years, German intelligence officers had dismissed reports of American bombing accuracy as propaganda, as exaggeration designed to demoralize German forces and mislead tactical planning. The device before Vorwald proved those dismissals catastrophically wrong. The Americans had not exaggerated. If anything, they had understated their capability. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics contained within this 70-pound assembly of aluminum, brass, and precision optics would force German leadership to confront an uncomfortable truth. Germany had lost the air war not through lack of courage, not through insufficient fighter production, not through tactical errors that better planning might correct. Germany had lost because American industry had solved bombing accuracy at a scale and sophistication that German engineering had not even attempted. The war would continue for more than 2 years after Vorwald's examination, but the outcome was already determined by the technology sitting on the examination table before him. The story of how America came to possess this capability begins not with military requirements, but with a single engineer's obsession with precision. Carl Lucas Norden was born in Java in 1880, the son of Dutch parents working in the colonial administration. He studied engineering in Switzerland at the Federal Institute of Technology in Zurich, where he absorbed the Swiss precision engineering tradition that emphasized tolerances measured in thousandths of an inch and mechanisms built to function perfectly under varying conditions. After immigrating to America in 1904, Norden worked for various engineering firms before joining the Sperry Gyroscope Company in 1911. At Sperry, Norden encountered the gyroscopic stabilization systems that would become central to his life's work. Gyroscopes, devices that maintain orientation regardless of external movement, had been used in ship stabilization and torpedo guidance. But Norden recognized their potential application to aerial bombing. An aircraft moving at 200 miles per hour at 20,000 feet presented targeting challenges no existing sight could solve. The bombardier needed to account for aircraft altitude, forward velocity, wind speed and direction, the ballistic properties of the bomb itself, and the movement of the target if attacking ships or vehicles. Calculating all these variables manually while the aircraft maneuvered to evade anti-aircraft fire was effectively impossible. Norden believed a mechanical calculator combined with gyroscopic stabilization could solve these problems. In 1920, he left Sperry to establish his own company, partnering with Theodore Barth, an entrepreneur who secured contracts with the United States Navy. The Navy sought improved bombing accuracy for attacks on enemy ships, a mission requiring precision that existing bomb sights could not provide. Existing sights were essentially telescopes with rudimentary range-finding capabilities, requiring the bombardier to estimate variables and time bomb release by judgment and experience. Accuracy varied wildly depending on crew skill, weather conditions, and combat circumstances. Norden spent the 1920s developing the fundamental mechanisms that would define his bombsight. The gyroscopic stabilization platform maintained level reference regardless of aircraft pitch, roll, or yaw. The telescopic sight provided a magnified view of the target below. The mechanical calculator, consisting of gears, cams, and precision bearings, computed bombing solutions based on inputs from the bombardier. The automatic pilot connection, perhaps the most revolutionary feature, allowed the bombsight itself to control the aircraft during the bomb run, eliminating pilot error from the final approach to the target. By 1928, Norden had produced the Mark III bombsight, the first design that demonstrated the concept's feasibility. The Navy tested the device aboard observation aircraft, achieving accuracy improvements that validated Norden's approach. But the Mark III remained too complex, too fragile, and too expensive for widespread deployment. Norden spent the next 5 years refining the design, simplifying mechanisms where possible, improving reliability, reducing production costs. Each iteration brought marginal improvements in accuracy and operational suitability. The Mark XV bombsight, the version that would enter full production in 1941, represented the culmination of this development effort. The device weighed 65 pounds in operational configuration, consisting of the stabilization platform, the optical sight head, the calculating mechanism, and associated control boxes. The bombardier interfaced with the system through a series of knobs and dials that allowed input of critical variables. Aircraft altitude was set manually based on altimeter readings. Airspeed came from the aircraft's instruments. The bombardier estimated wind speed and direction based on visual observation of ground movement during the approach to the target. Once these variables were set, Norden calculated the exact moment when bombs released from the aircraft would strike the intended target. The system accounted for the bomb's ballistic trajectory, falling in an arc determined by initial velocity, altitude, air resistance, and gravity. The telescopic sight provided 28 power magnification, allowing the bombardier to identify specific buildings within a target complex from altitudes exceeding 20,000 feet. The gyroscopic platform maintained level reference even when the aircraft maneuvered, ensuring the sight remained oriented to the target regardless of aircraft movement. The autopilot connection, designated the C-1 autopilot in Army Air Forces terminology, allowed the bombsight to control the aircraft during the final bombing run. The bombardier would engage the autopilot approximately 3 minutes before bomb release, giving control of aircraft heading and bank angle to the Norden itself. The bombardier adjusted the sight's crosshairs to track the target during the approach. Norden's mechanical calculator continuously updated the bombing solution based on the rate of target movement across the sight's field of view. This rate, combined with the preset variables of altitude and airspeed, allowed the mechanism to calculate precisely when bombs should be released to strike the target. At the calculated moment, the Norden triggered bomb release, automatically, eliminating human reaction time from the equation. The bombs departed the aircraft's bomb bay in a precise sequence, creating a pattern of impacts that, under ideal conditions, would saturate the target area with explosive force. The United States Army Air Forces tested the Norden extensively during the late 1930s, conducting bombing trials at proving grounds across America. The accuracy achieved under test conditions was remarkable, exceeding anything existing bombsights could produce. Bombardiers using the Norden placed bombs within 100 feet of target centers from altitudes of 20,000 feet under controlled conditions, with no combat stress, no enemy opposition, and optimal weather. These test results, classified secret by military authorities, suggested that American bombers equipped with the Norden could achieve precision sufficient to destroy specific industrial facilities, rather than simply saturating target areas with bombs. This capability aligned with American strategic bombing doctrine as it evolved during the late 1930s and early 1940s. American air power theorists, influenced by the writings of Julio Duhay and other strategic bombing advocates, believed that air power could win wars by destroying an enemy's industrial capacity and civilian morale. But American doctrine differed from British approaches in one critical aspect. The Royal Air Force, particularly after the devastating losses of early war bombing campaigns, adopted area bombing, saturating entire cities with incendiaries and high explosives to destroy industrial capacity dispersed throughout urban areas. American doctrine emphasized precision bombing, striking specific factories, rail yards, oil refineries, and other critical industrial targets while minimizing civilian casualties. This approach was partly moral, reflecting American public opinion that opposed deliberate targeting of civilians, but it was also practical. Precision bombing promised to achieve greater destructive effect with fewer sorties and less risk to bomber crews if the technical capability to achieve that precision actually existed. The Norden Bombsight was the technology that made American precision bombing doctrine theoretically possible. When war came to Europe in September 1939, the United States remained neutral but began accelerating military production in anticipation of eventual involvement. The Norden Bombsight entered full production in 1941 as contracts were placed with manufacturers across America. The Victor Adding Machine Company in Chicago became the primary contractor, producing Nordens alongside their commercial calculating machine business. Hundreds of skilled machinists, trained in precision manufacturing techniques, assembled bomb sights in temperature-controlled facilities, where tolerances were measured in thousandths of an inch, and every component was individually tested before installation. Security surrounding the Norden was extraordinary, reflecting American military leadership's belief that the device represented a war-winning advantage that must be protected at all costs. Each bomb sight was serialized and tracked from manufacture through operational deployment. Bombardiers trained on the Norden signed statements acknowledging their responsibility to prevent capture of the device by enemy forces. Combat crews received explicit orders to destroy bomb sites if aircraft were forced down in enemy territory. The destruction mechanism consisted of a thermite grenade housed within the bomb site assembly, designed to melt critical components if activated. By December 1941, when America entered the war following the attack on Pearl Harbor, approximately 2,000 Norden bomb sights had been produced and installed aboard B-17 Flying Fortresses and B-24 Liberators. Production would eventually reach approximately 50,000 units by the war's end, making the Norden one of the most extensively produced precision instruments in history. But production numbers meant nothing if the device could not perform under actual combat conditions. The gap between test range accuracy and combat effectiveness would prove wider than anyone anticipated. The 8th Air Force began operations from British bases in August 1942 with attacks on rail yards in occupied France. Early missions demonstrated both the Norden's potential and the immense challenges of precision bombing under combat conditions. Weather over European targets frequently obscured visual bombing, forcing cancellation of missions or bombing through cloud cover by radar, which offered far less accuracy than optical sighting. German fighter opposition forced American bombers to fly in tight formations that limited individual aircraft maneuverability and complicated bombing coordination. Anti-aircraft fire, particularly the German 88mm flak, that could reach altitudes exceeding 30,000 feet, forced evasive action that disrupted the stable bombing run the Norden required. Mechanical failures occurred with disturbing frequency as gyroscopes failed, optical elements became misaligned, or calculating mechanisms jammed under the stress and vibration of combat flight. Despite these challenges, American bombers achieved accuracy that impressed both Allied observers and German defenders. Attacks on specific industrial facilities demonstrated that American bombardiers could place significant bomb loads within target areas, measuring hundreds of yards across from altitudes where German fighters struggled to intercept effectively. The accuracy was not perfect. Individual bombs frequently missed by hundreds of feet, even under favorable conditions. But the concentration of hundreds of bombers attacking simultaneously created destructive effects that began systematically dismantling German industrial capacity. German intelligence officers, analyzing damage patterns from American raids, initially dismissed the accuracy as statistical aberration or good fortune. Surely no bomb sight could achieve the precision these patterns suggested. Not from 20,000 feet, not through German fighter opposition and anti-aircraft fire, not with crews under combat stress. The captured Norden that reached Rechlin-Lars in March 1943 would force reassessment of every assumption German intelligence had made about American bombing capability. The B-17 Flying Fortress that carried serial number 73-5-2-1 departed its base in England on January 23, 1943, as part of a formation attacking the port facilities at Lorient, France, where German U-boats operated from heavily fortified pens. The mission was part of the strategic bombing campaign against German submarine warfare capability, targeting the infrastructure that supported U-boat operations in the Atlantic. The bomber, assigned to the 91st Bomb Group, carried a crew of 10 men, including the bombardier, Lieutenant Robert Kearney, responsible for operating the Norden during the attack run. German fighters intercepted the formation over occupied France. Focke-Wulf, Foe 190s and Messerschmitt Bf-109s attacked from head-on and from above, tactics developed to avoid the B-17's defensive armament while striking vulnerable areas. The bomber took hits to engines and control surfaces, causing progressive damage that forced the aircraft to fall behind the protection of the main formation. Separated from mutual defensive fire support, the damaged B-17 became an isolated target for follow-up attacks. Additional hits killed the pilot and damaged hydraulic systems, making controlled flight increasingly difficult. The co-pilot, recognizing that the aircraft could not reach England, ordered the crew to bail out over occupied France before the bomber became unflyable. 9 crew members successfully evacuated. 8 were captured by German forces within hours and became prisoners of war. 1 evaded capture with assistance from French resistance networks and eventually reached neutral Spain. The bombardier, Lieutenant Kearney, removed the Norden's security cover and attempted to activate the thermite grenade before bailing out, but the destruction mechanism failed to function properly. The grenade ignited but did not generate sufficient heat to melt critical components before Kearney was forced to evacuate the burning aircraft. The B-17 crashed in a field northeast of Lorient. German troops reached the crash site within minutes, extinguishing the fires before they consumed the airframe completely. The Norden Bombsight, though damaged by fire and impact, remained substantially intact. German intelligence officers recognized immediately the significance of the capture. The device that American forces had protected with extraordinary security measures, the bombsight that enabled the precision attacks devastating German industrial facilities, was now in German hands for detailed examination. The bombsight was carefully removed from the wreckage and transported under armed guard to Rechlin-Lars, the Luftwaffe's primary test and evaluation facility located in northeastern Germany. Here, German engineers and intelligence specialists would spend months analyzing every aspect of the device's design, construction, and operational capability. Oberst Wolfgang Vorwald, assigned to lead the analysis, brought exceptional qualifications to the task. He had studied optical engineering at the Technical University of Berlin during the 1920s, focusing on precision optical systems for astronomical telescopes. He understood the mathematics of lens systems, the challenges of maintaining optical alignment under vibration and temperature variation, the compromises necessary in any practical optical instrument. After graduation, he had worked for Carl Zeiss in Jena, one of Europe's premier optical manufacturers, before joining the Luftwaffe in 1936 as air warfare expanded and Germany rearmed. Vorwald had spent the war's early years analyzing captured Allied equipment, from British bomb sites to Soviet aviation instruments, assessing foreign technology and recommending responses. But nothing in his experience prepared him for Norden. The sophistication of the mechanism, the precision of the manufacturing, the integration of gyroscopic stabilization with optical sighting and mechanical calculation exceeded anything German industry had produced or even attempted. Vorwald's initial examination, conducted over 3 days in mid-March 1943, documented the device's major components and operational principles. His report, classified secret and distributed only to senior Luftwaffe leadership, began with an assessment that would prove prophetic. The captured American bomb site represents engineering and manufacturing capabilities that fundamentally exceed our own. The device achieves operational accuracy through precision manufacturing at tolerances we cannot match with available German tooling and quality control. Replication of this device using German industrial capacity would be impossible at any meaningful scale. The implications for the air war are severe and immediate. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The detailed analysis that followed Vorwald's initial assessment required months of disassembly, measurement, and testing. German technicians photographed every component, measured every dimension, analyzed every material. The gyroscopic stabilization platform received particular attention. 2 gyroscopes, spinning at high speed and mounted in gimbals that allowed free movement in all axes, maintained level reference regardless of aircraft orientation. The gyroscopes themselves were precision-machined aluminum rotors, balanced to tolerances measured in 0.010ths of an inch, spinning in jeweled bearings that minimized friction. The gyroscopic platform maintained horizontal reference with accuracy exceeding 0.1 degrees, providing the stable foundation necessary for accurate optical sighting and ballistic calculation. German bomb sites used simpler stabilization systems, or relied on pilot skill to maintain level flight during bombing runs. The precision and reliability of the Norden's gyroscopic platform exceeded German systems by orders of magnitude. The optical sight head contained a complex arrangement of lenses and mirrors that provided 28 power magnification while maintaining image stability despite aircraft vibration. The sight features German optical engineers recognized as extraordinarily sophisticated. Temperature compensation mechanisms adjusted for thermal expansion of lens mounts, maintaining focus across temperature ranges from -40 to +120 degrees Fahrenheit. Anti-reflection coatings on all air-to-glass surfaces maximized light transmission and image contrast, technologies that Carl Zeiss had pioneered, but that American manufacturers had now matched or exceeded. The mechanical calculator represented perhaps the most impressive aspect of the entire assembly. A complex arrangement of gears, cams, and bearings performed continuous ballistic calculations based on inputs from the bombardier and feedback from the rate gyroscope that measured target motion across the site's field of view. The calculator solved differential equations mechanically, updating bombing solutions multiple times per second as conditions changed during the approach to the target. German engineers recognized the mathematical sophistication embedded in this mechanism. The cam profiles, the gear ratios, the bearing arrangements all reflected a deep understanding of ballistics, aerodynamics, and mechanical computation. Replicating these components using German manufacturing capabilities would require tooling that did not exist, quality control procedures that German factories had not implemented, and precision standards that German industrial culture had not prioritized. The autopilot interface, which allowed the bomb site to control the aircraft during the final bombing run, revealed another layer of American technical sophistication. The connection between bomb site and aircraft autopilot required electrical and mechanical interfaces that transferred control signals with precision and reliability. The system allowed the bombardier to make fine adjustments to aircraft heading and bank angle using controls on the bomb site itself, eliminating communication delays and pilot reaction time from the bombing process. German bombers had no equivalent capability. German bombardiers aimed weapons manually, coordinating with pilots verbally to adjust aircraft position during bombing runs. The human element in this coordination process introduced errors and delays that the American system eliminated entirely. As Vorwald's team completed their analysis through spring and summer 1943, the implications became increasingly clear. The Norden Bombsight represented not just a superior piece of equipment, but evidence of systematic American advantages in manufacturing precision, quality control, systems integration, and engineering philosophy that Germany could not match. The report Vorwald submitted to Luftwaffe headquarters in August 1943 contained technical specifications, detailed drawings, and recommendations for German responses. But the report's conclusion focused not on technical details, but on strategic implications that transcended the immediate tactical questions about bombing accuracy. The United States has achieved manufacturing precision and systems integration capabilities that exceed German industrial capacity by significant margins. The bombsight examined represents one example of this broader American advantage. We should expect similar American superiority across other military technologies, where precision manufacturing and systems integration determine performance. Our existing advantages in fighter performance and anti-aircraft artillery cannot compensate for the systematic destruction of German industry that American precision bombing will achieve over time. Germany lacks the industrial capacity to replicate American precision manufacturing at the scale required to achieve parity. We face an opponent whose industrial capacity, precision manufacturing capability, and systems engineering sophistication fundamentally exceeds our own. The report reached Hermann Göring, a commander of the Luftwaffe, in September 1943. Göring's response was immediate and dismissive. He ordered Vorwald's conclusions redacted from distributed versions of the report, insisting that suggestions of American industrial superiority were defeatist and undermined morale. The technical specifications could be distributed to relevant engineering teams, but the strategic assessment was forbidden from wider circulation. Göring's rejection reflected a pattern that would characterize German leadership's response to increasingly dire military intelligence throughout the war. Uncomfortable truths were dismissed as defeatism. Evidence of enemy superiority was reinterpreted as exaggeration or propaganda. Technical realities that contradicted preferred narratives were simply ignored. But reality does not adjust to convenient narratives. The bombing campaign that the Norden enabled would continue with increasing intensity, systematically destroying German industrial capacity, regardless of whether German leadership acknowledged American technological advantages. The 8th Air Force, flying from British bases, and the 15th Air Force, operating from Italy, mounted increasingly devastating attacks on German industry throughout 1943 and 1944. Oil refineries that produced synthetic fuel for German aircraft and vehicles were systematically destroyed. Ball-bearing factories that supplied critical components for everything from aircraft engines to tank transmissions were bombed repeatedly until production collapsed. Aircraft manufacturing plants were struck with precision that demonstrated the Norden's capability under actual combat conditions. The accuracy achieved in combat never matched the precision demonstrated on test ranges. Weather, enemy opposition, mechanical failures, crew fatigue, and combat stress all degraded performance from theoretical maximums. But even degraded Norden accuracy exceeded what German bombsights could achieve under any conditions. American formations placing half their bombs within 1,000 feet of target centers, from 25,000 feet, accomplished what German level bombers could not match from any altitude. By late 1944, German industrial production was collapsing under sustained American and British bombing. Norden had achieved exactly what Norden himself had promised 2 decades earlier. It had transformed strategic bombing from area devastation into precision destruction of specific industrial targets. The story of the Norden bombsight's impact on World War II extends far beyond the device itself. What Oberst Vorwald recognized during those months of analysis at Rechlin-Leers was that the bombsight represented the visible manifestation of a deeper American industrial capability that Germany could not replicate. The precision required to manufacture 50,000 Norden bombsights during the war years demanded manufacturing infrastructure, quality control systems, and skilled labor pools that took decades to develop and could not be created through wartime emergency measures. American industry in 1941 possessed advantages that German planners had systematically underestimated. The United States had spent the 1920s and 30s developing mass production techniques that combined high-volume output with precision manufacturing. American automobile factories produced millions of vehicles annually, while maintaining tolerances that European manufacturers associated only with low-volume luxury production or specialized equipment. This capability to manufacture precision components at scale translated directly into military advantage once American industry converted to war production. The Victor Adding Machine Company's production of Norden Bombsights exemplified this American manufacturing philosophy. The company employed machinists trained in precision instrument manufacturing, workers who understood that tolerances measured in thousandths of an inch were not exceptional requirements, but standard expectations. Temperature-controlled facilities maintained consistent conditions that prevented thermal expansion from affecting precision measurements. Quality control inspectors verified every component against specifications before assembly, rejecting parts that deviated from tolerances even marginally. Multiple inspection stages throughout the assembly process ensured that completed bomb sites met performance standards before military acceptance. German industry operated under different constraints and priorities. Precision manufacturing existed in Germany, concentrated in firms like Carl Zeiss for optics or specialized machine tool manufacturers. But German industrial culture emphasized craft production and specialized expertise rather than standardized mass production of precision components. A German optical instrument might exceed American equivalents in ultimate performance, but producing thousands of such instruments to consistent specifications challenged German manufacturing systems in ways that American factories handled routinely. The material requirements for Norden production further illustrated American industrial advantages. Each bomb site required aluminum alloys, brass components, precision steel bearings, optical glass, and dozens of other materials, all meeting exacting specifications. American industry supplied these materials in quantities sufficient to produce 50,000 bomb sites, while simultaneously manufacturing hundreds of thousands of aircraft, millions of vehicles, and uncountable other precision instruments. The logistics systems that delivered materials to factories, the quality control that ensured material consistency, the supplier networks that maintained production schedules represented industrial capabilities built over decades and impossible to replicate quickly. Germany faced chronic shortages of critical materials throughout the war. Aluminum production struggled to meet aircraft manufacturing demands, forcing compromises in bomber construction that limited payload capacity and operational range. Precision bearing production never achieved quantities adequate for military requirements, creating bottlenecks in everything from aircraft engines to tank transmissions. Optical glass production, despite Germany's historical leadership in precision optics, could not expand sufficiently to meet military demands for bomb sites, gun sights, rangefinders, and reconnaissance equipment. These material constraints meant that even if German engineers had designed a bomb sight equivalent to the Norden, German industry could not have produced such devices in meaningful quantities without diverting resources from other critical military programs. The trade-offs imposed by material scarcity created a cascade of compromises that degraded German military effectiveness across all domains. American industry faced no such constraints. The United States possessed sufficient industrial capacity to produce precision bomb sights, long-range bombers, escort fighters, and everything else required for strategic bombing campaigns while simultaneously supporting ground forces, naval operations, and allied partners through Lend-Lease. The Norden bombsight's effectiveness depended not only on manufacturing excellence, but on extensive training programs that prepared bombardiers to operate the device under combat conditions. The United States Army Air Forces established specialized bombardier schools across America, facilities where crews spent months learning the mathematics of bombing, the mechanical operation of the Norden, and the procedures for combat bombing missions. The training was exhaustive, reflecting the military's recognition that the bomb site's sophistication demanded equally sophisticated operator knowledge. Bombardier candidates began training with classroom instruction in mathematics and physics. They studied ballistics, learning how bombs fell through air and how various factors affected trajectory. They learned navigation, becoming proficient in map reading, celestial navigation, and dead reckoning. They studied meteorology, understanding how wind, temperature, and atmospheric pressure affected bombing accuracy. Only after mastering these fundamentals did training progress to actual bombsight operation. The Norden itself required hundreds of hours of practice before bombardiers achieved proficiency. Simulators allowed practice without consuming bombs or aircraft flight hours, teaching the mechanical operation of controls and the procedures for setting up bombing runs. But simulation could not replicate actual bombing, so training progressed to live drops on practice ranges. Bombardiers flew dozens of training missions, dropping practice bombs on target arrays, while instructors evaluated accuracy and technique. The training built muscle memory and decision-making skills that would prove essential under combat stress. German bombardier training operated under different constraints. German bombing doctrine had evolved during the Spanish, Civil War and early World War II campaigns, emphasizing medium bombers operating at lower altitudes in direct support of ground forces. This tactical focus meant German bombardiers trained primarily for attacks on battlefield targets, hitting troop concentrations, supply columns, and tactical infrastructure. Strategic bombing received less emphasis in German training, and the bomb sites provided to German crews reflected these tactical priorities. When Germany did conduct strategic bombing campaigns, particularly during the Blitz against British cities in 1940 and 41, German bombardiers operated with equipment and training inadequate for precision targeting. German bomb sites like the Luftwaffe 7 provided basic ranging and calculation capabilities, but nothing approaching the Norden's sophistication. German crews compensated through crew coordination and experience, achieving respectable accuracy against large targets like cities or port facilities. But precision attacks on specific industrial facilities, the kind of missions American bombers conducted routinely by late war, exceeded German capability, regardless of crew skill. The training disparity compounded equipment advantages. An American bombardier operating a Norden after months of specialized training could achieve accuracy that the most experienced German bombardier could not match with inferior equipment. The combination of superior technology and superior training created multiplicative advantages that widened as the war progressed, and American crews gained combat experience. The captured Norden that reached Vorwald's examination table in March 1943 arrived at a critical moment in the strategic bombing campaign's evolution. The 8th Air Force had been conducting operations from Britain for approximately 7 months, long enough to identify challenges but not long enough to develop complete solutions. Early missions demonstrated both promise and problems. American bombers could achieve remarkable accuracy under favorable conditions, but favorable conditions proved frustratingly rare over European targets. Weather over northern Europe limited visual bombing opportunities. Cloud cover obscured targets for weeks at a time, forcing mission cancellations or attacks through clouds using radar-equipped Pathfinder aircraft. Radar bombing sacrificed the precision that the Norden enabled, reducing accuracy to levels comparable with British area bombing. German fighter defences inflicted casualties that threatened the sustainability of daylight operations. Without escort fighters possessing range to accompany bombers to distant German targets, bomber formations fought their way through German fighter belts, losing aircraft at rates approaching 10% on deep penetration missions. The Schweinfurt raids of August and October 1943 illustrated these challenges with devastating clarity. Schweinfurt housed ball bearing factories producing components essential for German military production. Destroying these facilities would create cascading effects throughout German industry, disrupting everything from aircraft manufacturing to tank production. The industrial logic was impeccable. The operational reality proved brutal. Both raids penetrated deep into German airspace without fighter escort. German fighter units, coordinated by ground controllers using radar early warning, concentrated against the bomber formations with devastating effect. The first Schweinfurt raid on August 17th cost 36 bombers from a force of 230. The second raid on October 14th, known afterward as Black Thursday, lost 60 bombers from a force of 290. These loss rates exceeded sustainable levels. Bomber crews faced statistical certainty of death or capture if they continued flying missions at such attrition rates. The 8th Air Force suspended deep penetration raids pending deployment of long-range escort fighters that could protect bombers throughout their missions. Yet, even under these appalling conditions, the bombing achieved remarkable accuracy. Post-strike reconnaissance photographs showed bomb impacts concentrated on target facilities, demonstrating that American bombardiers using the Norden could place bombs precisely even under intense fighter attack and anti-aircraft fire. The Schweinfurt raids damaged ball-bearing production significantly, though not catastrophically due to German dispersal efforts and existing stockpiles. But the raids proved that precision bombing was operationally feasible if the bomber forces could be protected from unsustainable losses. The introduction of long-range escort fighters in early 1944 transformed the strategic bombing campaign. P-51 Mustangs equipped with drop tanks could escort bombers to Berlin and beyond, engaging German fighters throughout the mission profile. German fighter forces, forced to fight under conditions where American numerical superiority could be brought to bear, suffered catastrophic losses during the spring and summer of 1944. By late summer, German fighter defenses had been effectively suppressed, allowing American bombers to operate with casualty rates below 2% per mission. With fighter opposition reduced and bomber crews gaining experience, the precision that the Norden enabled began systematically destroying German industrial capacity. The oil campaign, launched in May 1944, targeted synthetic fuel plants producing gasoline and diesel for German military forces. These facilities, concentrated in relatively few locations and requiring complex chemical processes, were ideal targets for precision bombing. Attacks mounted throughout summer and fall. 1944 reduced German fuel production by more than 70%. By winter, fuel shortages grounded the Luftwaffe, immobilized panzer divisions, and crippled Germany's ability to conduct mobile warfare. Transportation attacks beginning in September 1944 struck rail yards, bridges, and canal systems that moved materials and finished goods throughout German industry. Precision bombing of rail facilities proved devastatingly effective. Destroying specific bridges or marshalling yards created bottlenecks that disrupted entire regional rail networks. By early 1945, German industry faced collapse not from destruction of factories, but from inability to move raw materials to production facilities or finished goods to military forces. The strategic bombing campaign achieved its objective of destroying German war-making capacity, and the Norden Bombsight was the technology that made precision strategic bombing possible. Vorwald's analysis of the captured Norden in 1943 had recommended that Germany acknowledge American technological superiority and adapt strategy accordingly. His recommendations included dispersing critical industries to reduce bombing effectiveness, accelerating fighter production to contest American air superiority, and developing advanced air defense systems that might offset American advantages. Some of these recommendations were implemented. German industry did disperse, moving production to smaller facilities scattered across occupied territories and building factories in underground sites protected from bombing. But dispersal created new problems. Moving production from integrated facilities to scattered sites reduced efficiency and increased transportation requirements. Underground factories provided protection from bombing but suffered from inadequate ventilation, lighting, and working conditions that reduced productivity and worker morale. The transportation systems required to move materials and components between dispersed facilities became themselves vulnerable to precision bombing, creating exactly the bottlenecks that dispersal sought to prevent. German fighter production did accelerate dramatically during 1944, reaching peak output in September, when factories produced more than 3,000 fighter aircraft in a single month. But increased production could not compensate for unsustainable pilot losses, fuel shortages, and the overwhelming numerical superiority of Allied air forces. German factories were producing fighters faster than pilots could be trained to fly them, and the trained pilots were being killed faster than training schools could replace them. By late war, newly produced fighters sat on airfields without fuel or pilots, rendered irrelevant by conditions that manufacturing alone could not solve. Advanced weapons development consumed resources that might have been better invested in conventional systems. Germany pursued jet fighters, rocket-powered interceptors, and sophisticated guided missiles, achieving technical successes that demonstrated German engineering excellence. The Me-262 jet fighter achieved speeds and performance that conventional aircraft could not match. The V-2 rocket represented a technological leap that would influence post-war aerospace development for decades. But these advanced systems entered service too late and in too few numbers to affect the war's outcome. Resources invested in advanced development might have produced more conventional fighters, more anti-aircraft guns, more trained pilots who could have contested Allied air superiority with available technology. The fundamental problem Germany faced was that the industrial war had been lost before the shooting war reached its critical phase. American industry's advantages in scale, precision manufacturing, resource access, and technological sophistication exceeded anything Germany could match or overcome through wartime emergency measures. The Norden Bombsight symbolized these advantages, but the advantages extended across every aspect of military production. American factories produced more aircraft, more vehicles, more weapons, and more of everything else required for modern warfare, all while maintaining quality standards that German industry could not match while under bombing pressure. The Norden Bombsight remained classified until 1945, when the war's end rendered secrecy less critical. The device that American forces had protected with extraordinary security measures during the war became known to the public through press reports and military histories. Post-war assessments evaluated the Norden's effectiveness with access to complete operational records, German damage assessments, and post-strike analysis impossible during wartime. These assessments reached nuanced conclusions about the bombsight's actual performance compared to wartime claims and post-war mythology. The Norden had not enabled perfectly precise bombing from high altitude. The mythology that bombardiers could place a bomb in a pickle barrel from 25,000 feet was propaganda, not operational reality. Combat accuracy never approached test range precision. Weather, mechanical failures, combat stress, and enemy opposition all degraded performance from theoretical maximums. American bombing killed hundreds of thousands of civilians in German and Japanese cities, despite doctrine that emphasized precision attacks on industrial targets. The moral distinction between American precision bombing and British area bombing was less clear in practice than in theory. Yet the Norden had achieved its essential purpose. It enabled precision bombing accurate enough to destroy specific industrial facilities, precise enough to create cascading effects through enemy industry, reliable enough to equip 50,000 bombers and conduct hundreds of thousands of combat missions. American strategic bombing, enabled by the Norden and the industrial might that produced it, systematically destroyed German and Japanese war-making capacity, contributing significantly to Allied victory. The device worked well enough, under conditions difficult enough, to accomplish strategic objectives that determined the war's outcome. The lessons Vorwald had drawn from examining the captured Norden in 1943 proved prophetic. Industrial capacity, technological sophistication, and systems integration capability determined modern warfare's outcomes more than traditional measures of military strength. The nation that could manufacture precision instruments at scale, that could train operators to exploit sophisticated technology, that could sustain operations through superior logistics and industrial depth, possessed advantages that battlefield courage or tactical excellence could not overcome. These lessons would shape Cold War military development as surely as they had determined World War II outcomes. The precision bombing technology that began with Carl Norden's obsession with mechanical calculation would evolve into satellite-guided campers, munitions achieving accuracy measured in feet rather than hundreds of feet. The integration of computing, optics, and guidance systems that Norden pioneered would develop into the precision strike capabilities that define 21st century warfare. But the fundamental principle that Vorwald recognized in 1943 remained unchanged. Wars between industrial powers are won in factories and laboratories before battles are fought on battlefields. and technological advantages rooted in industrial superiority create military gaps that cannot be closed through courage or determination alone. The metal cylinder that Oberst Wolfgang Vorwald examined in March 1943 represented more than a bomb sight. It represented the industrial might of a nation that could manufacture precision at scale, the technological sophistication of engineers who solved problems others had not attempted, and the systematic advantages that determined the Second World War's outcome. Vorwald understood these implications immediately, even as his superiors dismissed his conclusions as defeatism. History would prove him correct, though Germany would endure 2 more years of devastation before the truth he recognized became undeniable to all. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.